Hi, welcome. On this part 3, we will learn how to derive the half-time equation for a second order reaction. Hopefully you have seen part 1 and part 2. And so let's go ahead and remember the definition of half-life, or T1/2. So it is a time required for the concentration of a reactant to decrease to half of its initial concentration. Having said that, we can move on and start. Okay, so now let's move on to our concentration time equation for a second order reaction. So this is what we have. So again, we're solving for T first, and then we're solving for half-life. Okay, so let's see what we got. So we have 1 over current concentration T, and then we will just move this one to this side, minus 1 over initial concentration would equal to K times T. Yes, everyone good so far? Okay, so let's go ahead and solve for T. T would equal to 1 over current concentration minus 1 over initial concentration, and these will be all over K. So right now we have solved for for T, but we want to simplify our numerator because we want to make our life easier. So let's go ahead and do that. Well, we can actually leave it like this, and then we would go ahead and try to solve for T1/2 for half-life. So as we know, this is true for every order of reaction because it's the same definition of half-life. So whenever we have T, it's going to be T1/2. Our current concentration, it's going to be our initial concentration over 2. So let's go ahead and change these little things. So let's rewrite our equation. Let me get another color. Okay, so we would have T1/2 equals to 1 over 1, yeah. Because 1 over 1 is going to be 1, so we have a numerator of 1. And our numerator, it's going to be initial concentration over 2. So remember our cool trick we learned before? Minus our 1 over initial concentration. And this is going to be all over K. So let's go ahead and try to simplify our numerator. So remember, the ones that are located on the outside are going to be our numerator, and the ones on the inside are going to be our denominator. Sorry. Okay, so let's go ahead and rewrite our formula. So we would have 1 times 2 over initial concentration minus 1 over initial concentration over K. Very good so far. So let's go ahead and try to simplify it once more our numerator. So let's go ahead and write t 1/2 is, it's going to be 1. Okay, yeah, so we have the same denominator right here in our numerator. Okay, so that might be sound a little bit confusing. So yeah, so right here, we're focusing in our numerator. So our numerator has the same denominator, which is initial concentration. So we just need to do a simple subtraction. So it's going to be 2 minus 1, it's going to be 1. So 2 minus 1 is going to be 1. So 1 minus, 1 over initial concentration divided by K. And K has a denominator of 1. So let's go ahead and apply again these cool trick we learned before. So it's going to be 1 over K times initial concentration. So let's go and see, okay, so this will be our formula. So let's go ahead and see the table if we got the same formula. So yeah, we got the same. Okay, so note that a half-life of a second order reaction is inversely proportional to the initial concentration. So yeah, so I don't know if you remember, but inversely proportional means that it's going to be 1 over the value. You're saying it's inversely proportional, which is true because you have initial concentration as your denominator. And this result makes sense because the half-life should be shorter in early stage of the reaction when more reactant molecules are present to collide with each other. Hopefully this video has helped you to understand better on how to get our half-life equations based on our concentration time equations of the different order of reactions.
If you like this video and haven't watched part 1 or part 2, I would recommend you to do so. Also, please subscribe to Hydrogen Bonds Are Fun and follow us on our Instagram page. Thank you.